Good afternoon, everyone. This is John Galbraith. I'm in the process of beginning the webinar for today. This is going to be part of the intermediate series. We typically start at about 12:05. I usually give people just a few minutes to get settled right at the beginning. I'm going to turn on the chat feature in case anybody would like to send me a message. So are people hearing my voice now? Great. Okay. Wonderful. Thank you. All right. There's all kinds of tricks about using this software, and I'm getting used to some of them, and others I'm not quite as good at yet. A couple of reminders before we get going. I'd like to ask people to mute their microphones, please, so that we don't hear any background noise. And also, if you have your webcam turned on, there's really no need to have that turned on. I don't have mine turned on. However, this session is being recorded with both video and voice, and then that will be posted to a special website that we're in the process of setting up right now. And that website will be a collection of every webinar that I've presented, so that if you miss one or would like to see some that are offered at different levels, then you can go to that website and get caught up. If you have any technical problems or other problems, let me know during the presentation, and copy Mark Sumner on the chat message to let you know. One thing that we're going to do is we're going to have a couple of quizzes today, and I think that'll be fun. I think it'll be a way to break up the webinar, and then also to give people a chance to chime in and chat. I do hear that somebody again does not have their microphone muted, so if you wouldn't mind, please muting your microphone, and you do that by finding your name on the list of participants, and then you click on the microphone icon next to it. And if you're muted, the microphone will be red, and if you're not muted, then it will be black. Okay. All right, I think we're ready to begin then. Today is the first intermediate level webinar that I presented. I determined this sequence of webinars by putting out a survey tool. And that survey is available, and during this session you have the option to, or after, you have the option to go to the survey and complete it, and it's pretty short. It's a wish list, like going to a restaurant, and it's a wish list of topics, and by letting me know what your main interest is, then I can make sure that I'm presenting material that you want to hear, and also at the level that you'd like to hear it at. So also, if you have requests for on-site training or other suggestions, that gives you a way to communicate with me. And so far, we've had over 55 people respond to that. So it's available to you during the recording or after. All right, let's go ahead and begin talking about physical weathering and soil formation. And this picture on the left shows bedrock that's been exposed at the surface. And in between the rock fragments, you can tell that they all fit together pretty nice and tightly at one time, just like a picture puzzle. But notice now that there are gaps between the rocks, and some of the rocks are actually missing, the rock fragments. In between them now, you see smaller particles, and this is soil. And you can actually see a small plant beginning to sprout in the crack where the soil is, and that's where also the available water would be and available nutrients. And so this is the beginning of soil formation, And that's how it starts, and it starts with physical weathering. All right, physical weathering is a series of processes that act on the parent material of a soil. And what is a parent material? Well, that's the material that it's either bedrock, sediment, or soil from which new soil forms. So sediment, an example might be the material that's moving around at the bottom of a stream. And soil that gets eroded from one part of the landscape and redeposited in a different part of the landscape, or maybe the soil gets moved by a bulldozer or some road building machinery or a garden shovel. In any case, anytime soil is moved from one spot to another spot or rock is moved, that becomes the parent material from which new soil forms. And physical weathering acts upon the moved material first. All right, here's a picture of the New River Valley near Blacksburg. And here is an example of 3 different parent materials. On the ridge tops, we can see this material would be what's called residuum. In other words, it resides in its original location. So the soils that form from residuum form from the material that's directly beneath them. And all of these ridge tops and narrow and steep slopes are going to be covered with residual soils. Colluvium, on the other hand, is the material that moves down the slope into a foot slope type position, as seen in the center of this photograph. And on these more gentle slopes, the transported material comes to a spot where it's in equilibrium, and so it stops moving. It collects. So residuum resides, colluvium collects. And then soil formation begins. Alluvium, on the other hand, would be this area covered with snow in the bottom of the picture. And this is a river floodplain and a river terrace system. And this is the New River. And this alluvium accumulates when the water leaves the riverbed and deposits material on either side of the stream channel itself. So residuum resides, colluvium collects, and alluvium accumulates. Well, what happens during weathering in humid soil, or in other words, in the soils like we find in Virginia, where moisture is abundant and we have a fairly warm climate, warm enough at least for weathering processes to take place? Well, for one thing, we get decreases. The particle size, in other words, the size of individual particles gets smaller. As weathering takes place, particle size decreases. As weathering takes place, the cementation of bedrock decreases. It becomes less cemented. The material becomes less dense. It becomes less fertile. The pH drops. And the stability of the primary minerals decreases, and that leads to chemical weathering. And that'll be a different subject that we cover later on. All right, but we also get increases when we get weathering. The porosity increases. Think of how dense a piece of bedrock is. There's virtually no holes in it. But as the bedrock weathers into soil, the porosity increases, the number of pores between the particles. The soil structure starts to develop and increase. The clay content increases, and so do other secondary minerals increase over time as weathering proceeds, and so does soil depth, or in other words, the depth to a root limiting layer such as bedrock. All right, and here's a nice picture that shows the 2 forms of weathering, and that's physical weathering and chemical weathering. Physical weathering, another word for that is disintegration. In other words, the rocks and soil particles are literally just spread apart, and then loose particles are removed by wind, water, ice, gravity, or any combination of those, erosion. We can see in the picture of the right an example of physical weathering where this bedrock is separating into smaller fragments. Also, if you look closely at the crack system, you see some red stains. That is the beginning of chemical weathering, and you note that it's taking place right on the edges that are exposed. So this is a nice picture that illustrates both. We will not talk about chemical weathering in this presentation, but we will in one of the next. Excuse me. All right, physical weathering. The main result is a decrease in grain size. Remember, we talked about a decrease in particle size. And the result of decreasing the grain size is that we greatly increase the surface area exposed to chemical weathering. We saw the chemical weathering taking place on the cracks between the rock fragments in the previous slide. So as those rock fragments get smaller and smaller, there's greater and greater surface area exposed to chemical weathering. Then we have physical forces that act on the particles, and they are at an equilibrium with the energy and the forces around them. In other words, the physical forces act on the rocks until the equilibrium is reached. And then the physical weathering comes to a stop or a pause, because as soon as any part of that equilibrium changes, then the physical weathering is rejuvenated again. So take it, for example, a rock that is exposed at the top of a cliff at the top of a mountain. Well, there's a lot of potential energy at work trying to move that rock to a lower position on the landscape. All right, as long as it's on top of that mountain, it eventually reaches an equilibrium with the forces being applied. Well, let's say then we get a small landslide takes place, and that set of rocks rumbles down the side of the hill and settles in the lower foot slope position. So now we have changed the equilibrium, and now there'll be more physical weathering take place now that some part has changed. All right, we have examples of both igneous and metamorphic rocks. We have crystals, individual crystals. And on the left, you can see a picture of granite. And you can see that it has very large crystals, and it also has multiple different minerals. On the picture on the right is a picture of basalt. And there are small grains that look at first to be like sand grains, and they eventually may become sand grains. But right now, those are simply very small crystals of different minerals. The chemistry of both of those rocks is the same. The only difference is the grain size. Well, if we have larger crystals, then that is going to slow down the physical weathering. If we have small crystals, it speeds up physical weathering. The reason is the surface area. The larger crystals have less surface area than the smaller crystals. Now let's think of an example of sedimentary rocks that are held together by strong cements, something like iron oxides. The stronger the cementing agent that's holding the sand, silt, and clay together, the more resistant that rock will be to physical weathering. If the sedimentary rock is held together by very weakly cemented material, then the grains will fall apart rather readily. Well, let's talk about the processes now. And this is the number one. So remember this one for a quiz later on. Rocks form under heat, weight and pressure, great heat, weight, and pressure, oftentimes rocks form very, very deep in the earth. The exception would be the rocks that form when magma rises up very close to the Earth's surface. But for most of the rocks, they form thousands to tens of thousands of feet below the surface. And they're under all that heat and energy and overbearing weight pushing down on them. Well, as those rocks, they may form at 10,000 feet of depth, but at some point, erosion brings them to the surface. And when they get to the surface, all of that weight that was pushing down on them is gone. And so we've changed the equilibrium. And when we remove the heat and pressure, then the material expands. It also cools, and that helps in the expansion. And that process is called unloading. So expansion after pressure release is the precursor to all other physical weathering. In other words, first thing we do is we take the pressure off the rock. Then it starts to expand. Then other physical weathering can take place. In massive rocks where there's really no layering, and like granite, a rind develops and peels off. And you can see a picture to the right is one that I took in Central Texas at Enchanted Rock. And it shows a very, very large upwelling of granite that formed underneath the ground surface, and now it's exposed above the ground. All the soil has eroded off, but you can see the big slabs that are parallel to the surface, and as pressure is released, this rind develops and cracks off. In all of these processes, we're decreasing the particle size. All right, let's talk about expansion and plucking. During the unloading process, we have macropores, and that's a fancy word for cracks that form between different layers of rock, different fragments of rock, or individual crystals in the rock. Now, what can happen then for physical weathering to move those rock fragments apart or move those crystals apart? One thing is salt water. If salt water enters the crack, then salts crystallize. And the expansion force of growing mineral crystals is enormous. It's very, very large. So the precipitation of crystals between or in the cracks between rocks helps push them apart. Ice oozes out of a confined space, so that's one that really does not do much work. If you pour water into a crack between two rock fragments, it will just simply form ice that moves outside the crack as it expands and onto the ground or into the air. But ice formation is not enough to separate rocks. It may push them slightly apart, but it cannot cause new cracks to form. The same is true with fungal hyphae and fine roots of plants like grass roots. The one exception is that woody roots of certain tree types have the ability to widen existing cracks. The ice, the fine roots, and the hyphae cannot really do much work as far as pushing rocks apart, but woody roots can push them apart, but they, again, do not cause new cracks to form. Another phenomena that you may have seen is when falling trees, when trees fall, if the roots have been growing into a solid bedrock layer, when the tree falls, it pulls up bedrock fragments with it, and it pulls it loose from the other. That's a form of physical weathering, because you're moving fragments of rock out of their original position. Fire or extremes in temperature like we get in the desert and in the Arctic. They may cause water or air that maybe got trapped in one of those cracks to expand rapidly enough that when it widens, it pushes those macropores apart just a little bit. Now that would be the cracks between rock layers or crystals. Again, it is not going to crack minerals in half, but it may separate between the minerals where they already have a surface. Well, here's a picture now to go. I've done a lot of text. Now let's get to some pictures. That's going to be a little more interesting. So on the far left, you can see a tree that grew in between two fragments of what used to be one individual rock. Again, that tree did not crack those rocks, but as that trunk expands, you can see that it is pushing the loose rock fragments further and further apart. Center on the top row, you can see a rock in the desert. And one thing that's true in the desert is you get extremes of temperature, and you also get salts in the air. And when those salts land in the cracks that already existed on this piece of bedrock that was exposed at the surface, every once in a while you get condensation or even a light rainfall. It wets up the salts that blew in and landed in those cracks. The salts form new crystals, and that helps push the fragments apart. On the lower left, you see a piece of rock where it's evident that salt water has settled into an existing crack and salts have crystallized and pushed that rock apart. And then on the right, you see a tree that has massive root systems growing into and between bedrock fragments, and when that tree falls, which it eventually will, it will pull those rock fragments out of the bedrock, and that is called plucking. All right, here's a question. Are we separating fragments or are we fracturing them? So when we separate individual crystals along the edges where the two crystals come together, that is more likely to happen than actually fracturing through the center of the crystal. The fracturing through the center of a crystal or a rock takes place more often when rocks fall from a high elevation and land on other rocks. So you have seen in the mountains of Virginia places where we have piles of rocks that come rumbling down the side of the mountain, or where we have rock overhangs at the tops of the ridges, and sometimes individual rocks fall off and land on a debris pile of rock below. And when they do, then you can actually fracture rocks into pieces. But this is the only example that I can think of other than actually hammering or striking a rock with a hammer. And I found by my experience that when I do this, if I look at the surface of the two broken pieces, most of the time I can see that they have already had a crack in that place. And all I really did was just help separate the rock where a crack already existed. And I can usually tell that because there's usually some iron or manganese or some other mineral staining the surface. And of course that had to have happened a long time before I hit it with a hammer. Now, wave action is one thing that may move loose particles off of rock surfaces. Again, the waves themselves are not going to break rocks apart, but if there are loose pieces, they can certainly move those loose pieces off. All right, and here's some pictures of rocks with their layering, and you can tell that some of these rocks are going to fall off, and when they do, they may splinter or fracture, but most of the work of physical weathering is going to be just to simply separate these rocks along existing surfaces where they have already begun to come apart because of unloading of pressure. We see time after time existence. Here we see that if those rocks come apart along the cracks that already exist, then the waves can move the rocks away. All right, so just for fun, let's take a short break and let's open up the chat line and let's take a quiz. And this is just for fun, so answer it silently, and then you'll know in your heart that you got the right answer. So what is more likely to, for these things, for fire, salt, roots, and ice, what is more likely for them to do? Do you think that they would split rock crystals in half? In other words, fracture the rock crystals, or do you think they would simply push them apart where there's already an existing crack? And again, I'll just let you answer that one on your own, and in a minute I'll go over the answer. Okay, I see some people are actually answering it, and the people that answered correctly. Here's a question that I've got is, your last slide said the opposite of your narrative. Okay, so apparently I have made a mistake here. Well, I'll have to take a look at mine and make sure that I didn't contradict myself. But if I did, then I apologize, and I'll try to make sure that that gets straight. How do you break, I guess, bedrock up to gain the benefits of the nutrients and use it for gardening? I'm assuming this question may also apply to soil. How do you break up, like, large clods of soil or particles of soil? So I think the biggest question is, in the physical weathering, what we're really doing is taking the pressure off of bedrock, allowing more and more cracks to develop. And as those cracks develop, then the fragment size gets smaller and smaller and smaller. And then chemical weathering is what releases the nutrients and converts minerals from one type into another, removes the cement between the rock particles, and actually allows it to go all the way to soil material. So physical weathering is probably not the way to release nutrients. However, I am aware that in certain countries, like in Indonesia, they have extremely acid soils. And what they do is they mine granite out of the quarry and they crush the granite. So these are fresh crystals of what are called primary minerals. They're loaded with nutrients. They crush those crystals, and then they spread that as a form of fertilizer on the soils to increase the fertility level of the soils. But it's a very slow release process, not something you would get instant benefit from like some of the commercial fertilizers. Okay, let's see if there's any other questions. Are geodes a manifestation of cracking rock by salt crystals? Very good question. We'll try to have a geology lecture later in the semester. I'm sorry. My semester is about to start here in a week. But we will have a geology lecture later in the webinar series. Geodes form when there is a void in the bedrock and when groundwater or other liquid moves into that void, and then crystals grow by precipitation. So this would be similar to hanging a string in a glass of salt water, and eventually salt crystals start to form on that string. In this case, the crystals that form geodes form on the outside edges of the void, and then they get larger and larger and grow toward the center. And then, of course, years later, when they're exposed at the surface, then we can crack them open and see what's inside. And one last question, it says, would seeding with granite help acid sulfate soils? Well, that's an interesting question. I'm not quite sure that it probably would not. The biggest thing about acid sulfates, and that is going to be, again, a separate webinar, is that we have to raise the pH and we have to prevent the material below from being exposed to oxygen. So if the area's been drained, we need to restore the water level. If it's been exposed by earth moving, then we need to cover it with enough soil and put it on a slope where it won't erode away, that soil. And then eventually, over time, weathering and raising the pH with some type of lime amendment is one of the ways to reclaim those soils. All right, well, let's go ahead and get started with the last half of our lecture here. Let's talk about abrasion. The more sharp, pointed, or flattened the particle is, the larger the surface area exposed to chemical weathering. So round particles have the lowest surface area, and so that's the most stable shape in nature. Minerals on the outside edge and along the open cracks begin to weather, and they begin to lose their cementation, and that forms what's called a weathering rind. After a weathering rind forms, if the transportation of the rock by either ice or water takes place, then the rock particles that are being transported hit against each other, and it breaks off the weathered loose material on the outside edge. In other words, it breaks the weathering rind off, and then a new weathering rind begins. And the farther the rock fragments have to travel, the more often they develop weathering rinds and the more rounded they become. And that's why big rivers have mostly rounded rocks, like the James River. Most of the rocks are highly rounded. Headwater streams may have a mixture of sharp and rounded rocks, and uplands with flat bedrock beneath have the fewest rounded rocks. Here's a picture of weathering rinds. And this is the fresh raw minerals on the inside on the far left, and the more reddish color is where those minerals have changed and chemically weathered into oxides and other secondary minerals. And then some of the cementation has been lost. And I don't know if you can tell, but the thickest part of the weathering rind is typically right where the sharp edges of the former rock were. Well, as this rock, if it would get moved a long distance, then these edges would be broken off, and eventually the rock will become rounder and rounder. And we can see that example here is a rock that is already rounded in the center on the bottom, and now it's developing a new weathering rind, and so this rock will become even more round when that new weathering rind is broken off. Other examples of weathering rinds, and you can see that they get broken off just like the bedrock did in the picture of the granite earlier, just a different scale. Here we can see a rounded pebble, and this is taken from a stream, and you can see the rounded sand grains that surround it. So as this rock fragment has been moved in the river, the weathering rind is continuously knocked off by collisions with these sand grains and other rocks. And this is what a pile of abraded gravel looks like. And again, some of these are fairly sharp or flattened still, skipping stones they look like, but others have obviously undergone quite a bit of rounding over time and have probably gone through multiple cycles of weathering rind development and then abrasion. Here's an interesting picture of where wind has taken this sand that is here in this desert valley and blown the sand particles, and they have literally scoured this bedrock that's sticking up out of the ground. And you notice it's more scoured closer to the ground. That's because these are very large sand grains, and it's very hard to pick them up high in the air. And so they typically hit the lower part of this rock more often than they hit the top. Here's a picture where wind and sand have hit this rock and polished it on this side, and then you can see what the original surface would have looked like in the downwind side where it's not polished. These are called ventifacts, and vent means wind. And so these are fragments that have been polished by wind striking them with sand grains. And here's the final quiz. The most common form of physical weathering is what? Either A, unloading, another word for that is expansion, or fracturing, splitting crystals in half. So again, just answer to yourself. I forgot to give you the answer to the first quiz. The answer to the first quiz was B, and the answer to this quiz is A. Unloading is the most common. Now, just before we end, does anyone have any questions that they'd like to ask through the chat line? Okay, today's presentation was offered at a little bit higher level than the previous presentation. There were fewer slides, but maybe more explanation. And that's an example of what the intermediate level of presentations will be. Again, I didn't throw a lot of facts and figures out there. That's what the advanced level will be, and tomorrow will be an advanced level presentation of this same slide set, although I will add more to it. I'd like to thank everybody for being here today. It's just about closing. I don't see any questions coming in, so either I lost my audience or answered everything perfectly clearly. I'd like to thank you for attending. Take a few minutes to fill out that survey if you haven't done so. Let others know about this webinar series if you'd like to share. It's open to everyone. And thank you for the nice comments. I enjoyed giving this presentation today, and I hope you learned something, and maybe some of these pictures will bring back some good examples for you if you're explaining this to other people. So otherwise, have a good day, safe travels, and we will sign on again tomorrow for the advanced level, and this will be one where for people that are looking for CEUs, trying to pass certification exams, and looking for a college, a senior or maybe even graduate level presentation on physical weathering. All right, have a good day, and we will see you down the road.